Okay, so for this video, I'm going to solve the first example from the first module that I have sent you regarding the first topic for this ECQ period. And it's actually talking about the impedance modeling. Um, and it's basically a way for you to solve for um, any voltage or current basically in a given circuit, but you're going to be solving them in S domain. So before we're going to start, let me just remind you how you're supposed to model your passive elements in S domain. So from your notes, for resistances, there's really nothing new about resistances because as you've seen, if you're going to model them in S domain, the R remains R. So which means to say if you have 2 ohms, that's still 2 ohms in S domain, so no problem with that. However, for your inductance and your capacitance, there are actually two ways for each how you can model them in S domain using impedance modeling. And for your inductance, one involves a series combination, right, of an inductance to a source. However, I hope you have noticed that the polarity of the source is actually opposite that of the polarity of the inductance caused by the current passing through it. And the model should be the inductance is labeled as Ls, whereas your voltage source is labeled as L times IO. We have talked about these variables also in your module, namely your IO and VO. Those are simply your initial values, and IO stands for the current through your inductance at time equals 0, or it's basically the current from the previous state of the circuit. Another model which can do is that which makes use of a current source, and for your current source you have two branches. One is your inductance again, which is now going to be Ls, and the other one, this is now your IO over S. There. Also take note that these two currents should be additive, so they must be of the same direction. I'm talking about the current through the Ls as well as the current from the current source. They must be of the same direction. However, again, talking about your initial values I of 0, take note that for the first example, so we will now be doing the first example for this video, it starts at an open position. So it states that the start or the beginning of time equals 0, is the moment when you short or you close your switch. Meaning, at the previous state is when the switch was still open. And you can now ask yourself, is there a current passing through the inductance when the switch was still open? And obviously the answer there is no, none. So if there is no current passing through the inductance, then your initial value is 0. So this is what comes after that. That means that this, therefore, the value of I of 0 is 0, which means to say this voltage source is treated as a short circuit, because that's the way it is, right? It's if a voltage source has a value of 0, then it's similar to a short circuit. So if this is short circuit, then you will now be left with just the LS, right? Similarly, if you will use the current source model, if your initial value here is 0, then the current source here has a value of 0, meaning it's equivalent to an open circuit. So if this is open, then you will be left with simply a branch containing LS. In short, if I of 0 is 0, or if you do not have an initial value, then the impedance model for an inductance is simply a branch whose value is LS. Okay? So I hope we're clear on that one. So the first thing you're supposed to do is to draw the circuit in S domain. So we can now draw the circuit in S domain. Actually not quite yet, because of the voltage source. You're given the voltage to be equal to 12 volts, right? And it's in DC. How do I know that it's in DC? Because of the symbol of the source. So the source looks like that, and the value is 12 volts. So it's a DC source. So looking at this, it's actually voltage as a function of time, which is equal to 12. And this one actually suggests that the value of voltage with respect to time is 12 all throughout. It's not changing. Meaning to say, this 12 is a unit step, and you can refer to our previous discussions from the prelims what a unit step is. But cut the story short, to get the S domain equivalent of 12 in DC, 12 unit step, take the Laplace of that, it's 12 over S. Okay? So from there, we can now draw our circuit. So we have here a source which has a resistance. Probably that is the internal resistance of the source. So this is the resistance, and this is the voltage. Remember, we have to draw the circuit in S domain. So the voltage here must be 12 over S. The resistance, remember, is still R. So the resistance here is 1. We'll still use 1. Nothing will change. Similar to the coil at the load, I'm just assuming that it's a coil because it's made up of a resistive and an inductive element. So the coil here has a resistance of 2 and an inductance of 200 millihenry. Now the 200 millihenry should become LS in S domain. So 200 milli is 200 times 10 raised to negative 3 multiplied to S. So let me just check. Yes, so that is our circuit. And we are being asked to solve for the current passing through this circuit. So obviously, current coming out of the positive terminal here using conventional flow should have that direction. And there. So since everything is in S domain, The first thing we will be able to solve for actually is the current also in S domain. So it's I of S. Don't worry because um, we can perform later on your inverse transformation to be able to come up with the final answer for current, which is now going to be in T domain. There. Okay. So the good news about solving circuits in S domain and using the impedance model is that you could actually make use now of any of the network laws and theorems which you have learned from your previous subjects, apply them, and solve for whatever you are trying to solve as if you're just doing numbers that are not, or functions that are not in S domain. So, like, say for example, for this circuit, how do you basically solve for a current passing through a given circuit? It's a single loop circuit. It's very simple. You are given the voltage of the lone source, you don't have other sources, and then you have the impedances of the circuit. So isn't it that you could actually solve for the total circulating current here by just simply Ohm's law, by dividing the total voltage with the total impedance? So that's exactly what we're supposed to do as well. So if I want to solve now for the current in S domain, wait, sorry. If I want to solve now for the current in S domain, I can just simply do that. So 12 over S, that's our total voltage, must be divided by 1 plus 2 plus 200 milli is the same as 0.2. There. So all we have to do now is to convert this in time domain. But as you all know, it's not going to be that simple because we still have to rearrange this function. So I will rewrite the equation as 12 divided by S multiplied to 0.2S plus 3. So this is now just simple algebraic manipulation that I'm doing. Now, from what we have learned from inverse transformation, we are now looking at a repeated linear function at our denominator. So supposedly we are bound to separate these two factors at the denominator for it to be transformable. However, we have to prepare the factors also because we do not have a form 0.2s plus 3. Or we do not have a form which looks like a 0.2s plus 3. The shortcut for this is actually just get rid of the denominator of s, of the highest degree of s. So just get rid of this coefficient, I should say. Just get rid of the coefficient of s. And we can do that by factoring out the coefficient. So this will be s times 0.2. So now that I've factored out the 0.2, I will be left here with s plus 3 over 0.2, which is equal to 15. There. Continuing the simplification process, I could also divide 12 by 0.2, which is now going to give me 60. So this now becomes 60 over s times s plus 15. And we can now do our partial fraction expansion from here. So this will be A over S plus B over S plus 15, which will now become 60 is equal to A times S plus 15. So remember, we are now cross multiplying this denominator to the right side of the equation. So if we cross multiply this to the first term, S gets cancelled. So my E1C S plus 15 and then plus B times S. Next thing, of course, is equating your coefficients. So we start with the highest degree of S, which happens to be 1. So what are the coefficients of S? At the left side, we have none. So this is 0. At the right side, we have A and B. So can't solve anything yet from that equation, so we continue. So decreasing your coefficient, or your exponent rather, s raised to 1 to s raised to 0, we therefore need now to take coefficients of s raised to 0, or those are simply your constants. So constants, left side is 60, right side we have 15a. There. So I'll just continue here. So from the second equation, it's very obvious that a now is 4. And from the first equation, this tells you that b must be the negative of a, so b is negative 4. Hence, your current in S domain is now 4 over S minus 4 over S plus 15. The final step is to convert that in T domain. So current in T domain, inverse Laplace, these terms are directly transformable, so I would assume no problem in transforming them. This is simply 4 minus 4 e raised to negative 15 t. Okay, so this is now the solution for the first item.